So this is actually chapters 1 and 2 in the textbook. You don't have to rewrite that top part. You just wrote it down. The study of compounds in which carbon is the principal element. Organic compounds contain carbon covalently bonded to other elements, primarily hydrogen. So you'll notice this involves a lot of carbons and hydrogens. Not all carbon compounds are considered to be organic. So the very simple ones like carbon monoxide and carbon dioxide and carbonate and bicarbonate and cyanide, they're not considered organic. We're talking about large groups of carbons bonded together, not just these single carbons. Carbon is special because it can form 4 covalent bonds. Carbons can get together and they can form chains, elongated chains. They can actually wrap around and form rings. The benzene ring being an example of one, but there's many examples. So we need to be able to kind of categorize these groups of elements. When we have a specific group of atoms arranged in a specific way, we call it a functional group. And that's how we classify these organic chemicals. We put them in groups based on certain ways in which they bond together. Members of the same organic family have similar physical and chemical properties, and that makes good sense because they'll have similar orientations of their elements, and that's due to their functional group. So we're going to be talking about different functional groups as we go ahead and learn about them. Here are some examples of some functional groups. The presence of a double bond. That's a distinguishing feature in an organic chemical, and therefore we say it's a functional group. Functional meaning it provides the way it behaves, its function, the way it exhibits properties. A triple bond would be a functional group. If we have atoms that are other than carbon in the structure, those will be functional groups. Essentially, it's anything that isn't carbon singly bonded to other carbons or hydrogens. Like I said, if you've got a bunch of carbons and hydrogens bonded together and they're all single bonds, everything is very symmetrical, it's very nonpolar, and there's nothing distinguishing about the molecule. As soon as you add something that isn't carbon, you now have electronegativity differences, you have dipoles, you've got a distinguishing location in the molecule. If chemical reactions take place, they tend those other atoms to be literally electrostatically attracted to those differences in the carbon chain. So if there's no differences and they're all single bonded carbons, something that's kind of around it that's going to bump into it, it bumps into it, nothing exciting happens. But if we've got something like a carbon-oxygen where oxygen has a high electronegativity and it's got a little dipole moment, maybe it's got a little negative charge to it, then that thing will be attracted to it. If it's positive, it's going to be attracted to it. And there's going to be reaction possible. So functional groups are also areas of higher reactivity. Let's now talk about the simplest family of organic chemicals. And they're called hydrocarbons. So this little flow chart here is a breakdown, and you don't need to put it in boxes. That was just the easiest way to create the flow chart. This is a breakdown of the way we name hydrocarbons. So essentially hydrocarbons can be broken down into 2 subgroups. Those 2 subgroups are called aliphatic hydrocarbons and aromatic hydrocarbons. So let's look at aliphatic. Aliphatic are essentially chains and rings, but they're not the benzene ring, all right? The benzene ring, keep in mind, looks like this. We've already drawn it a couple of times, right? And this is that type of notation that I introduced you to. All of the edges represent carbons, and they've got alternating double bonds, all right? And the other way in which we wrote it was, again, that hexagon, and instead of drawing it as a resonance structure, we put a circle on the inside to represent the fact that that pi bond is spread all over those carbons. It's like the smallest little piece of graphite that you could imagine. That's benzene. Aliphatics are essentially either chains of carbons or rings of carbons, but not this special ring shape that has alternating double bonds. It's the alternating double bonds that makes it special. So let's start today by looking at the alkanes, the simplest of the simple. Okay, so now let's talk then about alkanes. Alkanes are the only group of hydrocarbons that essentially has no functional group. It's all carbons singly bonded to other carbons or hydrogen. They're all sp3 hybridized. They're highly symmetrical. They're not exciting. Alkanes are what we call saturated hydrocarbons. It's because they don't contain any double bonds, and when something has no double bonds, it means it can be filled right full of hydrogen. So when we say that a hydrocarbon is saturated, we mean that it's saturated with hydrogens. It has as many hydrogens bonded to it as possible. The next class I teach organic chemistry, we're going to be looking at something that has double bonds, the alkenes, and we say that they're unsaturated because you could break that double bond and add a couple more hydrogens. So when they talk about things like saturated fats, a fat is a particular type of functional group. It's a special group of atoms on the end. And when they say that the fat is saturated, they mean that the chain of the fat is full of hydrogens. It means it contains no double bonds. You can't put any more hydrogens on it. It's saturated with hydrogen. Many people, when they hear the term saturated fat, think of like a sponge dripping in fat. And they say, ooh, that's gross. Saturated fat, that's gross. But people have no idea that the term saturation has nothing to do with a lot of fat or filled with fat. It has to do with the carbon chain on the fat molecule being full of hydrogen. That's what a saturated fat is. We name them by ending them with ane, and so now we've got to learn the prefixes in order to name these things. We use a prefix to designate how many carbons there are in a chain. So this is our introduction to naming. So yes, if you've taken the biology, you know that one carbon atom will start with meth, two carbon atoms will start with F, and the ending is ane in this case. So I'll have something called methane and ethane and propane and butane and pentane. And actually after 5 it makes some pretty good sense. Pentane, pentagon, hex, 6, hept, 7, oct, 8, non, 9. Before that it doesn't make sense. You've got to memorize the first 4. Okay, so meth, F, prop is 3, you just got to kind of remember it. That doesn't say but. It eventually will have an E on the end, so we call it bute. So we've got things like butane, all right, so it gets a U sound. Pentex, hept, oct, non, et cetera, et cetera. All right, let's now go with a bunch of examples. Again, you don't need the grid. This is just me putting some spaces. All I need you to put are the headings, so number of carbon atoms, and the first one we're going to deal with is 1, because we're going to work our way through some of the naming, all right? And then structural formula, which I'm going to soon kind of forget about. I'm only going to do the first couple of them on the structural formula. It's the condensed structural formula that I'm really interested in, because that kind of squeezes everything in. By the way, the structural formula on that computer was when all the H's were hanging out there. That's a big ugly picture. And then the condensed structural formula, we kind of collapse the H's in on their C's so that we can take a look at what the molecule is. It makes more sense to think of it that way. then the chemical formula itself, and then what we call the thing. And actually, I might even jump back and forth. If I'm talking about the simplest one, and it's got one carbon, what's this going to be called? Methane. Yeah, so this is called methane. Methane. And structural formula, carbon, hydrogen, 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 hydrogen. And you can see it's a pain to draw all these hydrogens, especially on this device. All right? I'm going to draw these things as being flat. We know that these are sp3 hybridized and they're tetrahedral shaped, and that all of the dipoles will cancel out. We just did that in our last unit. We've got to keep those pictures in our minds. Condensed structural formula. If I collapse all these down, the structure isn't much. CH4, because I've collapsed the H's onto the C. Chemical formula, CH4. Not exciting whatsoever. Methane is the lightest of all hydrocarbons. It's what we use when we use natural gas, all right? It's what comes out of the taps when we run our Bunsen burners. If you've got natural gas going into your house and you cook with natural gas, that's what you're burning. 2, you're using methane. Ethane. Carbon, carbon. Hydrogen, hydrogen, hydrogen. You get the idea. I hope when we get going on this, you're just drawing it. You're not necessarily looking at me, because you're just adding a bunch of H's. Condensed structural formula. We want to maintain the chain structure, so we write this as a CH3 bonded to a CH3. So we can still see our 2 carbons, and we can see that they're connected with a single bond. By squeezing everything together, we get C2H6. Next, 3. What's it going to be called? Propane. That's the stuff you use in your barbecue. Propane. All right? Ethane is also found in natural gas. Actually, natural gas is a mixture of the two. Propane, because we're getting longer and more carbons, the London forces are greater. They're a little more stickier. Propane is a gas, but if you squeeze it hard enough, you can get it to be a liquid in a tank. So it's actually a liquid in the tank, and then as it comes out into the atmosphere, it expands and becomes a gas as it comes out into your barbecue. So as you can see here, yeah, I don't, sorry. You can go to the bathroom and grab something, or you can just use a paper towel. CCC, expanded structural formula, what a pain. We got to put in all these H's. Why do they? The convenience of the propane is that it can easily be put in a tank as a liquid. That makes it portable. You can put natural gas in a tank, but because its London forces are very weak, you need high pressure, super high pressure, so you need a super thick tank, which isn't practical for propane, like barbecuing around your house. It's convenience. Question, Joe?
I was just wondering, would that be what the difference between octane and hexane is when you got the gasoline at too high hexane, you get detonation in your engine?
That's a good question. Is it because it's more volatile because it's lighter? You're talking about knocking, like a pre-ignition situation. Yeah, it's not as good of a mixture. I'm not exactly sure if that's the exact reason or not. I really have no idea. But you're right in that different qualities of gases will have different vaporization temperatures, and therefore they could behave differently in an engine. But I'm not sure if that's the exact reason.
100%
octane, yeah. Yeah, and so as soon as you've got a mixture in there, it's going to change their properties. But I'm not 100% sure if that causes that problem that you're describing. Yeah. Okay. Notice I've collapsed them down for the condensed structural formula. We can see that there's 3 C's, and we can put our chemical formula C3H. How many are on there? 8. Notice every time I add a carbon, what's happening to the number of H's? I'm going up by 2 because now I'm adding, notice I'm adding a CH2 group in the middle, because every time I'm adding it to the middle, it's got to go into that chain and it expands it out. Okay, I have more on the next page. So 4. We're not going to 10. We're not going to 10. Just relax. Sheesh. I'm not doing the structural formula anymore. We get the idea. Lots of H's. Condensed structural formula. CH3, CH2, CH2, CH3. Formula, C4, H10. Excellent. What's this called? Yeah, it's called butane. Now, we're come to an interesting point. This actually is called N-butane. And it stands for normal butane. No, this one is the only one at this point. What I'm trying to say is that I could have added this third carbon. Instead of on the end of the chain, I could have actually added it to this carbon up here to produce this situation. C, 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 all right? And then my last C up top. Now I'm going to add my H's in. When I draw structural formulas, condensed structural formulas, for different molecules, and I'm not sure what shape I want to draw it, I leave the H's off. And then when I'm done my shape, I add enough H's in to give the carbon 4 bonds. So let's take a look at this carbon. How many bonds does it have right now? So how many H's will it have? Okay, very good. Excellent. 3. So now I stick in a little H3. How many bonds does this carbon have? So how many H's will it need in order to get filled? Just 1. And I'm glad you're getting impatient with me because it means that it's pretty obvious, and that's an important thing. I've had some students struggle with this. How many H's is this guy going to get? 3. And this guy? 3. All right. So what's the formula of this thing? C, how many C's? 4. It's going to be the same thing. Very nice. What we've encountered is an example of what is called a structural isomer. All right? I've got a definition for isomers on the next page, but isomers are when you have 2 molecules that have the same chemical formula but different structural formulas. They are actually different chemicals. We cannot consider them to be the same thing. They will have different melting points and different boiling points. They will combust at different temperatures. They will behave differently. And connection is everything in terms of organic chemicals. The different connection produces a different chemical. Now I've got to introduce to you a new naming system. So we're getting to the point where we're going to be ready to name some more complicated ones. This particular molecule, and the way we name more complex molecule, is we first name the chain that we have, the longest chain, and this is a propane chain. It's got 3 in its longest chain. And then it's got this branch up here. Now this branch is made up of 1 carbon. You might think it's called a methane branch. But as soon as you put it as a branch, you don't call it methane anymore. You call it methyl. So a group that has a carbon and 3 hydrogens with 1 bond as a branch is called a methyl group. We're going to write all this stuff down in a moment. Actually, I've got a sheet that I'm going to hand out that has the rules on it, and we'll write it down in a second. So this is a methyl group that's attached to a propane. So this is called methyl YL propane. Methyl propane. That's fun. All right. Now, I'm ready to talk about 5, and I don't think I have enough spaces to write it because my next page has general formula. So I might have to erase this number 4. I'm actually going to erase this right now. Everybody got that information about methylpropane? So we've got 2 isomers of butane, N-butane and methylpropane. Now I'm going to erase this page. What's that? They're both butanes. They're both examples of butane. So just to say butane would cause a chemist to go, okay, oh, the only thing I know is there's 4 carbons and 10 hydrogens. Which one are you talking about? So you got to either call it N-butane, and you can't just call it the other butane. N-butane and the other butane. I don't think that would be a good naming system. So we name it based on chains and connections. When we say propane, you know how to draw 3. When we say it's a methyl, we know we have to put 1 in the middle. I couldn't put it on the end. Let me just show you one thing. Hold on. Quit asking. I can't just put it on the end. There's too many what-ifs right now. Hold off on the what-ifs. If I were to put the methyl right there, let's say I were to put that right there, and that becomes a 2, and that becomes a 2. It would still be C4H10. You're right, then it's N-butane. The reason this is still N-butane is because all of these bonds can rotate. This molecule, in reality, if you could see an N-butane right in front of you, it's got all kinds of kinetic energy in it. Because it's got temperature and it's warm, it's wiggling and jiggling. You can think of the bonds like being little elastic bands. Imagine trying to connect a bunch of eggs, I don't know why I said eggs, to elastic bands or springs, right? It would, it would just kind of wiggle and move all over the place, right? And then if you could do that in outer space, like imagine that Chris Hadfield's doing this, so there's no gravity. And then you let this chain of 4 eggs connected by some springs or elastic bands, you just let it go. We could all imagine, because we saw some videos of Chris Hadfield, we could all imagine that it would go, right? It would just kind of wiggle and jiggle and move around. So whether I put that carbon on my picture as a straight line, or I put it up, it doesn't matter. As soon as I let it go, it's going to do that wiggling and jiggling, and it could rotate and think, okay, elastic bands can't rotate, but single bonds can rotate. Sigma bonds can rotate. So whether I draw it up or whether I draw it to the side, it makes no difference. That's still N-butane. Again, they're trying to derail my recording. They're killing me here. Crazy stuff here. All right? So if I put it on the end, it's no good. All right. Let's get rid of all this stuff. Oh, I'm ignoring Bailey today. It's Bailey. It's Rebel Bailey. She came in late. She's usually here at like 7 o'clock in the morning. And Bailey came in late today and is just looking to cause some trouble. All right. Again, I'm ignoring. So now I've got a lot of carbons to deal with. Like I said, I'm going to just go carbon, bond, carbon, bond, carbon, bond, carbon, bond, carbon. All right? And I've spilled into the other one, but that's okay. And that's because I'm going to be drawing all of these different isomers, all these different types of orientations. So once I'm pleased with this, 1, 2, 3, 4, 5, I can add my H's. How many go on the first one? H3. Next. H2, 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 and H3. Excellent. And the formula, C5, H12. Actually, we can always get the number of H's for an alkane based on the number of carbons. How do we get it? What's the thing that's connecting all these things? What do I mathematically have to do with my 5? What's that? Double, multiply by 2, add 2. That's the general formula. We'll write that down in a moment. This, by the way, is called N-pentane. N-pentane. N means normal. It simply means a chain. All right, let's now draw the other isomers. I think there's more than 3, so I might need a little extra room here. My plan when I draw isomers is to draw the chain, 1, 2, 3, 4. Now, I'm taking one of the carbons off of the end, and I'm asking myself, can I put it somewhere in the chain to make a different molecule? I've already said, if I put it on the end, what do I recreate? N. So no good. I put it on here. exciting. We're getting, frustration is growing. So I put it on this one. Excellent. H3, this guy up here, H3, down here, H3. Oops, that's an H2 in there. Oh, no, that's just an H. Woo! I'm flustered now because of all the criticism that's going on today. H2, H3. Excellent. Again, C5H12. We're not surprised at that. What's this called? Methyl butane. That's fun. Methyl butane. Excellent. Now, my next strategy would be to take this methyl group and move it on to the next carbon. But that's the same thing. If I flip that over, you'll notice I'll just have the same molecule except it's flipped over. And that is the same molecule, so that's not something new. So taking this guy, putting it here, I'm going to get the same thing. If I take this guy and put it on the end, I get the N-pentane back. So I'm kind of done moving around that particular methyl group. But I could take another methyl group off of the chain and stick it into the middle one and get kind of like a T, right? So there is only 3 on this one. I wasn't sure. So C, C, C. There's my propane chain. And now I'll put a methyl group there, and I'll put a methyl group there. And that is H3. No H's on the center guy. H3, H3, H3. Again, it's C5H12. It is the same formula, but different structure. And now I have 2 methyls. So I have to use some other prefixes in order to do this. What's that? No, I don't use an ethyl. An ethyl would be made up of a chain made up of 2 carbons, not 2 1-carbon chains. Okay? This is actually called dimethyl to represent 2 methyls. And what's the chain that I stuck this to? Nope, it's not a butane anymore. It's a propane, because there's only 3 in my chain. You could look at it as a chain up and down with 2 up the side, makes a difference. It's a propane. Propane. I apologize for squeezing that into the bottom. And that's the end of the isomers for pentane. You can imagine as we go to higher and higher numbers of carbons, we get more and more possible situations for isomers. Let's stop there and write down the general formula. Yep. CnH2n. I think we saw that trend. So if I was talking, and then again, I'll just give you an example. So we could simply say, what if we had C60? Because we could simply have a big long one. We're not going to name it, but how many H's would there be? 122, right, would be the formula. So next I want to define structural isomers, because I just talked about it. Structural isomers of a hydrocarbon have the same chemical formula, but a different arrangement of carbon atoms. The easy way to determine whether you've got structural isomers is to name them, and if the names are different, you will have 2 different molecules. The naming system has been created so that isomers cannot have the same name, so they're not confused. That's the way the naming system was designed. One last little slide here that finishes this particular lesson before I go on to this handout. Nothing to write here except one little piece of homework, but we can just leave it aside for now. Don't write this down, but this just indicates how the number of isomers grows when you have more and more carbons in a chain. So you'll notice CH4 was 1, and ethane was 1, and propane was 1, and butane was 4, and pentane was 3. But as soon as you get to 6, there's 5 of them. 7, there's 9. 8, there's 18 different isomers. And if we had something like C40H82, that's how many different isomers you could draw. And the homework I was going to ask you to do is draw the 9 isomers of heptane. All right? So write that down as homework under your structural isomers. Draw the 9 isomers of heptane. The 9 different structures that you can have with 7 carbons.